Yeah. Go web. Fly. Up and away web. Shazam. The new Spider-Man movie is coming up, and you can tell I'm excited. Anyway, I'm gonna be teaching you how to make this effect using only a marker, vanilla JavaScript, and HTML canvas. And if you're interested, I have a tutorial from a few years ago where you learn how to make a game inspired by Doctor Strange. He's in this movie too. In the game, you draw a free-form shape with this marker, and you need to draw a circle to open the portal. So if you're interested, check it out. But now, let's get started. We are gonna start with some basic HTML. I'm just gonna give the page a title in the head section, and in the body we will only have a canvas element. We're not gonna have more items inside the body really. And now if I refresh, this is empty, nothing here yet, but the canvas is actually there. It's just invisible. And you can also see that the body has a small border, a small margin there. And the canvas is not really centered or stretching the screen yet. So I'm going to now do these modifications in CSS. I'm going to link an external CSS file like this, where I'm going to remove the margin and set the black background to the body. And the canvas is going to be white on top, so we can actually see it. And I'm going to position the canvas to be in the center screen. So absolute positioning and 50% top, 50% left, transform, translate, -50%, -50%. And I really want this canvas to stretch the whole screen. So I'm going to put the width of 100% here as well. Now if we refresh, we see the canvas as white on black. The body is black now here. I'm not going to need these elements anymore. Let's go to the console. And let's go back to our HTML file and start to write some JavaScript. Usually I do this in an external file, and I will soon, but I'm going to add the basic functionality here in the HTML page. It's just going to access the camera. So I'm going to ask the media devices to get user media, and I'm going to be setting the video to true. We don't need audio here. This returns a promise, so we can write then. And here our callback function is going to get the parameter that is the raw data, the raw signal coming from the camera. And here we can use it. So we can, for example, define a video element like this. And I'm going to give the raw data as the source for this video and start playing. Now, at this point, the video starts playing, but there's not data yet necessarily. It can take a few milliseconds. So I'm going to write here unloaded data and specify to this another callback function like this. Inside this, I'm going to access the canvas by saying get element by ID my canvas. So this canvas here on the top, the one and only canvas that we'll use. And I'm going to set its width and height to be that of the video width and the video height, like this. So our canvas will be the same size as the video coming from my webcam. And to test, I'm going to quickly get the context object of the canvas, and I'm going to draw an image on it that covers the whole canvas. So it's going to start at 0, 0, the top left corner, and it's going to be the canvas width and canvas height. And it's possible that this get user media is going to fail, so we're going to catch here any error, and I'm just going to alert this on the screen. Now, if I go here and refresh and allow, it's going to ask to allow to use the camera. Then we get this static image of me now because I have a webcam right here. So basically, now we have a way to access the camera and display it on the canvas. And on the canvas, we're going to use a lot of image processing methods to get our effect to work. So let me now just go back here and import a few more files. These are just JavaScript files that are empty for now, but we are going to implement next. And I have two of them actually. One of them is this one for the web shooter effect. It's going to be the logic for making this effect. But I also have a utils file this time because some of the functions are really general and you can use them in a lot of different projects. So I thought it's a good idea to separate them and teach you a little bit about how to work with bigger projects this time. So I'm gonna remove this code here now. It was just for quick testing, and I'm going to define an object of the type web shooter effect. This is something that we are going to implement next, but I want to have it here already now, and it's going to need two things: a canvas to show the effect on, and a video element to take the input to do the processing from. So I'm gonna just have this in the HTML file here, and now we're gonna move to this web shooter JS file, and here we're going to start to write some code. So we define our web shooter effect class, and inside the constructor we are just going to set the canvas and the video as attributes. And I'm also going to get a reference to our context here by doing the same thing we did previously, and I'm going to store that as an attribute as well. I want it for quick access here, and it just makes sense. Now, we're also going to call here an animate method. This is something that we are going to define next. And this animate method is going to do the same thing we did previously. Draw the image from this video on this context, and the width and height of this image is going to be the canvas width and the canvas height. So same thing as previously to get the image to show on the canvas. But we are going to call request animation frame to call this animate method as fast as possible, many times per second. Usually this means about 60 times per second, but if your processor is slow, it's gonna do a bit less. But this effect is quite efficient, and I think it's gonna work quite fast on any PC nowadays. All right, but there is one problem when calling request animation frame like this, that it needs access to this element right here. And this won't be accessible anymore after you pass this to request animation frame. It's gonna change what this means. So the way we fix this is calling the bind method and telling it that this here is this. Hope it made sense. So now with our animate method in place and running here, I'm going to refresh, allow the camera, and now you actually see the live stream of me moving there as I speak. So it's running and we are ready to start to implement our effect. And I'm gonna do that by first thinking, how is this effect going to work? And really, the most important part is detecting this kind of marker in the image. And I'm not going to detect it as an object. I'm just going to look at the blue locations. They are special locations. There's no other blue in this screen apart from this marker. And I'm going to get these so-called marked locations next. That's what we're going to implement. I'm going to get these locations by calling a function called getMarkedLocations on this canvas. So I'm going to pass the context there. And let me log these marked locations in the console to test. Now this function doesn't exist yet. We need to implement it. And it's a general function. It can be used by many things, like the Doctor Strange video I mentioned previously. We also did it for Halloween in the torch effect video. If you haven't seen it already, do check it out. It's actually easier than this one. So moving now to the utils.js file, and I'm going to write here the getMarkedLocations function with the context passed as a parameter. And these locations are going to be an empty array for now, and we're going to put them there as we detect them, going pixel by pixel. So we get the image data from this context like this, and we specify here that it starts at 0, 0 and has the canvas width and height. So we're going to get the pixel information over the entire image, really. And I'm going to log this image data here for now and debug. We are not returning yet these locations, so marked locations is going to be undefined. But let's just test quickly. I'm going to go to the browser, refresh. And what we see here in the console is a log of image data. So this image data is one frame that came from my camera, and it has a width and a height of 640 by 480. But most importantly, this data element, it's in a long array over 1 million items. This number here is actually this multiplied by this and multiplied by 4, because this is actually an array of RGB and alpha values. So this is red, green, blue, and alpha of the first pixel, like the pixel in the top left corner, very small pixel there, has these red, green, blue alpha values. Then the next one to the right of it has red, green, blue, alpha, and so on. A lot of different pixels right there. Let's actually get the value of the top left pixel, the first pixel, like this. And you see here the value of the top left, like the first pixel in this image, which is this gray image background right here, seems to have a value of 120, 120, 130, something like that. So when these values are kind of equal to each other, it means that we are dealing with some kind of gray color. But if I'm going to move now my marker to that corner, you're going to see these values change. It's the value is kind of fluctuating a bit, but it's something like maybe 90, 190, something like that. So 0, 90, 190. It's 90 green and about 190, I think, for the blue. And transparency is always 255, so the maximum. And that's what we're going to need to detect next. We're going to need to detect some kind of blue color. I'm going to put here that the color we are looking for is about 0 red, 90 green, and 190 blue. But I'm also going to mention a threshold value. And that's because, as you saw here, the value is really fluctuating a bit. So we need to be more tolerant here and allow a little more values than this. So this threshold is going to help us with that. And I'm going to explain next how this is going to work, but let me remove this log and iterate through all of the elements in this data array. But notice here I'm incrementing I by 4 at each step. So I'm jumping over every group of 4. And here I can get, for example, the red component like this, the green component like this, the blue component like this. And I could also get the alpha component, but I'm not going to need it, so I remove it now. Now what we'll do is we will check if there is a color match between this RGB array and our color that is given up here as a parameter and the threshold that we have specified. If this is the case, then we are going to get the index of this pixel, which is very easy. It's just I divided by 4. We are incrementing I here in values of 4, so dividing by 4 is going to give us the index of the pixel in this array. And using this pixel index, we are going to find out the X and Y location of the pixels, of each pixel. And I'm going to teach you this by first pixelating this image so that I can explain to you a little better how it works. You need to see the pixels. So p index of 0, as I said, is this top left corner pixel there. And this p index increases all the way to the width of the image. And in this case, the value of 31 is over there, so this image has a width of 32. And it will increase again as it goes to the next row, like this, and go again to the end like this. So now we have 32 plus 32, giving us 63 because we are counting at 0, starting the counting at 0 there. And it really goes on like this, the p-index, all the way until the last pixel in the image. So how we get the width and height from this is actually quite easy. If we divide, I mean, not the width and height, but the X and Y location of any given pixel, we get it by dividing this pixel index right here by the width of the image. So if we divide this 167 by the width, which is 32 in this case, we are essentially going to get the height here instead. You can think about it as an area a little bit. And that's going to be a little bit over 5. But if we take the floor of that value here, then that's going to give us 5. And the index is 0, 1, 2, 3, 4, 5 if you count it is in starting at 0 there. So the Y value for this pixel is 5. And we just do this by calling the floor method because we want to work with whole numbers, and divide this by the width of the canvas. And for the X is actually important to look at this remainder value here. So when we divide the pixel index by the width, how much are we left with? So this remainder here of 0, 1, 2, 3, 4, 5, 6, 7 is what you get when you divide 167 by 32, which is the width of this pixelated image in this case. In our case, with the full resolution video, it's much larger, but I again pixelated this so that I could explain this formula better. So what we do is just take the remainder here using this modulo operator, and now we have the X and Y location of this particular pixel that happened to match. We don't have this color match function yet, but it's gonna be coming soon. So now we add this X and Y location to our location array, and let's return it because it's going to be needed when we are printing them to the console later. And now we have this color match function here to define. So we try to match C1 and C2 if they are close enough given a threshold. And to understand this, I'm actually going to show you this example of a RGB color space. So this is actually a 3D space right here with one example color that I can change with these sliders. So what happens is if you make this, if you move this slider to the right, then not only that the color changed by making it more red, but also the point changed by moving it more on the red axis. So what happens if you add also this green value, for example, here, the point now moves also on the green axis, and a point here corresponds to yellow color, which is a combination of this red and green in some amounts. But we're actually looking for some blue color. I think it was something like 90, 190, something like this. So let's see where this 90 and 190 color is. It seems to be somewhere here. So a little, somewhat on the blue axis and a little bit on the green axis as well. And we want to look at this with a given threshold. So that means that not exactly this color is what we're going to be using for our matching, but we will tolerate a little bit more colors around this. And we essentially accept any color inside this growing sphere that we have here under a value of, I have here 60 mentioned in code as some kind of example. The problem is if you put too high of a value here for the threshold, your sphere starts to contain also colors that you don't necessarily want to be there. Like now it really starts to look a little bit like green and reddish there. And if you really go all out with this threshold, it's essentially going to contain all possible colors. So this is like a full color cube now. But as we don't want to do that, I'm going to allow a threshold of, say, 60, like in what I wrote here in the code. Okay, so having said that, let's move back here and say that if the distance between our given color, so in this case this bluish color right here, or C1, and any color that comes from the pixels in the image, if the distance from that to the other is below a threshold, which is the sphere radius, then it means that we are inside of that sphere and we have matched to our key color that we are looking for. So if this is the case, then I'm going to return true. Otherwise, I'm going to return false. And this distance function is something that I have used all the time. It's essentially the Euclidean distance function between 2 points. In this case, it's 3D space. So I'm actually writing it using this for loop that will go first, 0 will correspond to red, then 1 to green, and 2 to blue. So when the length is going to be 3, then this is going to compute the Euclidean distance in 3D space. And I am probably gonna make a better video about the Euclidean distance in the future, but it's really just a diagonal of a cuboid where you have the points in 3D space and they are opposite in that cuboid. So you find this formula out by applying the Pythagorean theorem twice. And I'm writing it with the for loop actually because I'm going to be using this distance function later on these locations. And these are just 2D points here. So then this for loop will adapt and just use the first two dimensions because there's no third dimension. And really we are in the utils file, so this distance function could be useful for many other things as well. Like if you do machine learning, then this will adapt to use higher dimensionality data as well, and that's very useful. So let's have it like this. And now we have finally everything working here. I'm going to refresh. Okay, and you can see here marked locations as an empty array this time because we are actually returning something. It's no longer undefined there, but it's empty. So it's empty, but if we bring in our marker, something happens. And if I'm going to bring it just a little bit from the side, you can see only about 10, 30 locations, but you can probably tell that there are a bunch of blue pixels now in the image and 0 like this. So we just implemented a way to figure out if there is a blue thing in the image or not. I'm not sure if this is useful, but if the beast is gonna be creeping behind me, then I'm gonna find out in this way. Not the Disney beast, but the X-Men beast. Okay, so let's continue, and I'm gonna debug in a little bit different way. So if the locations are gonna be more than 0, then I'm gonna loop through them, and for each of them I'm going to draw them on the image to actually see where these locations are on the screen. I'm gonna draw them using white rectangles. So they're gonna be rectangles with one width and one height. So essentially I'm gonna be coloring each individual pixel with white, a pixel that should be blue. And I'm gonna just call the fill here, and let me close these and refresh. And now when I move the marker, you see that the blue locations are actually colored as white. And depending on your values for the color and the threshold, you may or may not get this. You may need to play a little bit with the threshold and with the value from here. So try it out because it really changes depending on the light in the room and on the camera that you use and things like that. Okay, so with these locations, the next thing that we're going to do is actually calculate the average of these marked locations. So we do that by calling our average function. And this is going to be a utility function. So I'm going to define this here below the distance. So given some locations, we're going to calculate the average location, or otherwise called the center of mass. And we are doing this by going through all locations and adding through to this center, to the x of the center, we add each location's x, and to the y of the center, we add the location y. So like this, but then we also divide each of these elements by how many locations we have. It's essentially the average value on x and the average value on y. Return, and going back to my web shooter class, I'm going to display this point as green, and I'm gonna make this into a circle, full circle, so starting at 0 degrees and ending at 360 degrees or 2 pi radians in this case. it has a radius of 10, and here I'm actually deconstructing the point, which is just an array. It's deconstructed into C of 0 and C of 1. So it's just a quick way of writing that JavaScript supports. So I'm gonna fill this and now refresh, and let's see where the center is. So it's there. The center is pretty much on the cap of this marker, but a little bit at the bottom, and that's because the cap of this marker is really big in comparison to this small part right here. So the center is not really in the middle of the marker, but much closer towards the cap here. It's really pulling it more in that direction. Okay, so that's fine. But to make this effect, we need 2 points. We need to figure out in which direction this marker is pointing. And 2 points define a line. And we can get the other point by calculating what is the furthest away point, marked location, from this green dot right here. And it's going to be something here where the base of the marker is, you see? Because this is so close to this marker cap that the farthest away location has to be here at the base of the marker. So let's see how we do that. It's nothing fancy really. We are just going to say here A is equal to get the farthest from, so the farthest location from C in this case. And this is going to be another utility function. Who knows when we need something like this again. And I'm writing it here in the utils. I'm going to say get farthest from, and here we get the maximum distance using our distance function, and I'm initializing this maximum distance to the first location here. We know there are locations here because we had the check earlier if the location's length is more than 0, so that's fine. And now we initialize this maximum distance as the distance from the point to the first one in the list. And let's say here the farthest point is also equal to the first one for now. And I'm going to iterate through all of them, all of the other ones, and say here that if the distance, this distance from the location to our center point, that dark green point, if this distance is going to be greater than the max distance, our max distance is going to update, and our furthest point is going to be these locations of I. Basically, we have found one point that is further away than the previous that we had. I initialized like this so that I don't deal with things like negative infinity or stuff like that. So I return here the farthest location. And let's go back to the web shooter and draw this location as well. I'm also gonna make this green, but maybe I'm gonna use a light green color for this one so that we know it's different. And now I'm drawing this in a very similar way to the previous one, and saving, refresh. And what we have now is 2 points showing on the marker. And we have the first one that we already are familiar with, but also this new one at the base of the marker. And this one is fidgeting a little bit because sometimes these pixels change, but that's not going to affect our effect too much. So it's nothing that we need to deal with in this video. But really, the important part to focus on is that these points never change place. So because the average is always going to be closer to the top of the marker, which has more blue in it, the farthest away location is always at the base. So if you think now about these locations, I call them here in code A and C. All we need to do now is shoot a web from A to C. These two locations don't only encode a direction, like a slope of the line, but they also tell us they also tell us the direction. So they are actually a vector in addition to telling us the slope of the line. So that's what we're going to do next, essentially. We are going to go back here and say shoot something from A to C. And this is going to be a new method here inside of our web shooter effect class. And we're going to be shooting at a given rate. I'm going to take the rate coming from the points, so the distance between the points on the x-axis, and I'm gonna actually divide that to make the animation look slower for teaching purposes. I'm gonna tell it to be divided by 10, for example, and I'm gonna calculate this rate on the x and on the y like this. So if I do this now, I'm gonna have a rate that is gonna be pretty much a tenth of this whole distance that I have here on the between these 2 points. And our web is going to be shooting at this kind of increments. So I put a smaller value there by dividing it by 10 so that we see the movement and we can debug it. But probably we want it to be faster than that. So let's see. And notice that I'm taking this distance because if we're going to be closer to the camera or farther to the camera, this distance is going to change. But we want our speed to stay constant. So that's why I'm defining this rate in relationship to how far these 2 points are from each other. And their relative distance changes depending on how far or close we are to the camera. So let's continue this and say here that we are going to be shooting some particles by adding a new particle from the from location, which is going to be this A. You can see here. So the light green dot in the image and with this given rate. Now these particles are an array. We need to go up here and store them inside our web shooter effect object and define the object. So we have a new object now called particle with a constructor that takes a location and a rate, a movement rate. We are going to store these as attributes right here. And have 2 methods. First, we have a method to update the location. So we are going to say that whatever the previous location is, move it, increase it by the given rate on X. And the same thing happens on Y. So I'm writing it like this. And the second method is going to be a draw method, which given a context, we draw these particles in the same way as before, but I'm gonna make them black to distinguish from the green marked locations from previously. And here, same code. Okay, now this is not enough. We still need to update and draw these particles. So I'm going to go up here and say update particles and draw the particles. And notice that I'm writing this outside of this if statement because the particles should continue to update and be drawn even if we don't have a marker visible on screen. Like maybe now I'm shooting something, but then I'm hiding the marker. I still want the particles to continue to move, the ones that have been shot out already. So it's important to keep these method calls outside of this if statement here. And let's define these. They are very simple. So the draw particles just goes through all of the particles in the array and calls the draw method for each of them with the given context, and the update particles in a similar way goes through all of them, and it's gonna call the update method. Right. And now we can test. Haha! Look at that. We have something quite interesting here already. So I can think of a bunch of things to do with this. And how about you guys? Comment below if you can think also of other stuff that you can do with this than web shooting. But I think it's really great already. And I'm gonna be trying more things with the marker in the future because I think it's such a simple object and you can do so many things with it, really. Okay, so now you see the points are being, the particles are being shot in the direction from this green, light green to the dark green. And as I'm moving this, it's leaving this kind of particle trail there. I think it's really interesting. You can do so many creative things with this. But let's make this, okay, actually before that, there is a problem with this because the number of particles increases. Let me show you. Here in the update particles, let's log the number of particles and refresh. And now you see as this marker stays on screen, that number continues to increase. And that means that even particles that are off screen, they are constantly adding more and more, and they are constantly being updated and drawn. We just don't see them because the canvas is in this area, but they do exist. So we need to take care of that, otherwise we have a memory leak. And I'm gonna do that by going here and saying that if our particle's location x is less than 0, or if the location y is less than 0, or if the x is gonna be greater than the canvas width, or if the y is gonna be greater than the canvas height. Then we are going to remove this particle because it's off screen. So I'm calling here the splice method and telling the array to remove one element at the ith position. But because when removing things in this array, what happens is that the rest of the elements following that item move back a step to replace it. It means that if we don't decrease here I, we may skip a particle that needs to be removed. So a new particle takes this step, but I increases, so it's going to skip this element. And this is really important to do, otherwise we can have some glitches popping up. All right, now here I'm just going to update the particles if they are still on screen. And let's save this, refresh, and now you can see that the number of particles stays somehow stable. It's 25, 26 now. If I'm gonna move more close to the side of the screen like this, then the number gets less because the particles disappear more quickly. If I move this marker all the way to this other side like this, then the number increases because the particles stay longer on screen. Yeah. Okay, we're kind of running out of time. I have another appointment next, but let me make this look a little bit more like a web. So I'm gonna remove this logging here, and let's have here a function for drawing the web. And this is going to go through all particles except the last one, and another for loop starting at I plus 1 and going to the end. So what I'm going to do is draw a line between every pair of particles here. So I do this by beginning a new path, setting a white style for the stroke, and moving to the particle, the ith particle location, and doing a line to the jth particle location, and doing the stroke. And we need to do this to draw this web up here where we are updating and drawing the particles in the same place, really. Now refreshing this shows something like a webby structure there. You can do many more things here, be more creative than what I'm doing now. And actually, I have also tried some different kind of strategy in a course. I think it was the Visual Web Development course of 2019. I had a different way for detecting the gesture to shoot the web back then. I had a fancy glove and more complex algorithms. There was some clustering based algorithms. I think it was agglomerative clustering method. But this method is much simpler to implement, and yeah, but anyway, the effect on top of the detecting the method from that course was different. It actually used physics, and when the web was approaching the side of the wall, like the side of the screen, it would attach, and then you could pull on it, and it was interesting, an interesting prototype. So check that out if interested. And there are a few things that I would still like to teach you here, but I don't have time now. So one of the things is that if I remove this marker from the screen and bring it back, you can see that there are some particles that are somehow appearing sometimes and moving slowly. So the problem is that when we are adding this marker and removing the marker from the screen, it causes this kind of blur, like the blue color is not, it's kind of blurry in fast movement, and this will happen if you don't make the marker show as fast as possible. But you can also avoid these kind of glitches appearing by delaying the effect a little bit. So as soon as you detect some blue coming, wait a fraction of a second and then start shooting. And you can find out how I did this by checking out my website. I have I'm gonna put the code there, and it's not very fancy really. I just don't have time to explain it right now. And I also have their implemented sound effect for shooting the web. And the sound effect is actually procedurally generated. It's synthesized using the Web Audio API. So check it out if curious. But also let me know in the comments if you really want to teach me those things or if the code is enough. But yeah, hope you liked this, and see you guys next time.